Good evening, ladies and gentlemen. This is lecture 8 in the series of lecture videos on Introduction to Econometrics, and today I am going to discuss regression without intercept, that is suppressing the intercept term. Then I will discuss the use of various functional forms in regression, and then changing scale and units of measurement in regression. Let me start with the regression equation, where the true relation is explained by this estimated regression, where y hat is equal to beta naught hat plus beta 1 hat and x, and these are the actual observation on y and x, and this is the regression line, the estimated regression line, and let us suppose this is the true relation. But we select a sample from the population, and we estimated the relationship by suppressing the intercept term. That in that case yi hat prime is equal to beta 1 hat prime x. Now the slope of the regression line where there is no intercept is higher than the slope of the regression line when there is intercept, the vertical intercept in the regression line. So such an effect potentially will produce bias for the betas, and it will inflate their t values. Regressing through the origin, the intercept term is absent or 0. So when we have a regression in which there is no intercept, either the intercept is absent theoretically, or its value is equal to 0. For example, yi is equal to beta 1 xi plus epsilon I, and its graph is like this. Vertically we measure the value of yi, and horizontally we measure xi, and this is the sample regression function with the estimated relationship like yi hat, and that is equal to beta 1 hat xi, and this is the rate of change of yi with respect to one change in x, and that is equal to beta 1 hat. And then the estimated model would be y tilde is equal to beta 1 tilde xi, or y is equal to beta 1 tilde xi plus epsilon tilde I. If we apply OLS to this, then beta 1 tilde will be equal to summation capital xi yi divided by summation capital xi square, and the variance of beta 1 tilde will be equal to sigma square hat divided by sigma xi square, and the sigma square hat is equal to summation epsilon I square divided by n minus 1. There are some of the features of the regression model without intercept. The summation of epsilon I tilde need not be 0. R squared on many occasions will turn out to be negative, and that may not be appropriate for the summary of statistics, and in that case we may not use R squared as the coefficient of determination. Degrees of freedom will not include the constant term, because when there is no constant term, then it will not be equal to n minus k minus 1. So without intercept model, the degrees of freedom will be only equal to n minus k. However, practically we must keep in mind that there is a very strong priori or theoretical expectation. Otherwise we will use or stick to the conventional intercept present model. So usually we will include intercept in the model unless there is strong theoretical arguments or theoretical expectation. Then we should not exclude intercept from the model. If intercept is included in the model but it turns out to be statistically insignificant, then we have to drop the intercept to run the regression. We here compare the regression with the intercept and regression without the intercept. Now in this case, beta 1 hat will be equal to summation small x small y divided by summation small xi square, where small x is in deviation form and small y is in deviation form. But if there is no intercept in the model, then beta 1 tilde will be equal to summation capital X and capital Y summation divided by summation capital X square. So these are not in deviation form. Variance of beta 1 hat will be equal to sigma hat square divided by summation xi square, where this x is in deviation form, whereas in this variance of beta 1 tilde, this x is not in deviation form. Sigma hat square will be equal to summation epsilon hat square divided by n minus 2, and in this case it will be equal to summation epsilon tilde prime square divided by n minus 1. Here the degrees of freedom are n minus k minus 1, where here the degrees of freedom are only n minus k because there is no intercept. And this is r squared, and this is r squared here. Here these are in deviation form, but these are not in deviation form. Let me take the example of capital asset pricing model. Security I's expect risk premium is equal to expected market risk premium. So this is the equation of expect risk premium, and this is for expected market risk premium. Beta 1 is a measure of systematic risk. If it is greater than 0, it implies a volatile or aggressive security, but if beta 1 is less than 1, then it implies a defensive security. The regression line of the security market line is like this. This is the slope. This is the expected rate of security on yi, and this is the curved interest rate parity. Another example, and international interest rate differentials equal exchange rate forward premium, that is this equation, and its graph is like this, the curved interest parity line. This is the slope, and this is the exchange rate forward premium, and this is international interest rate differentials. Here the expected value of alpha naught is equal to 0. If curved interest parity holds, alpha naught is expected to 0. So use the t-test to test the intercept to be 0. We can test this coefficient by using the t-test. Here is the computer output. Y is the return on a future fund in percent. The independent variable is return on Fisher index. This is method is least square. Total number of observations are 10. Without intercept, the coefficient of the model is 1.08, and it is significant. These are the r squared and adjusted r square, standard error of regression, sum of squared residuals, and so on. So formal report will be like this: yi hat is equal to 1.0899, and its t value is this. Its r square is 0.71, and n is equal to 10, and this is the standard error of regression. Standard error of regression is this 19.54. We test the hypothesis that beta naught is equal to 0. So we will test this with the help of this t-test. If this t-test p value is less than 0.05, then we will reject that beta naught is equal to 0. But if the p value is greater than 0.05, then we will fail to reject this. So in this case, we will fail to reject that beta naught is equal to 0. So we have this equation, and the t value shows that beta naught is statistically insignificant and different from 0. It is not equal to 0. Functional forms of regression. The term linear in simple regression model means that they are linear in the parameters. Variable in the regressions model may or may not be linear. If variables are not linear, we may make them linearized by transformation. But the important thing is that the model must be linear in parameters. If the model is not linear in parameters, then we don't call it a linear model. It will be non-linear model. Let us suppose the true model is non-linear and the population regression function is like this. It is going to increase, then it reaches maximum, and then it declines. And this is the relationship between income and age. So it means as age increases, then the income of the individual first increases, reaches a maximum, and then it decreases. But the sample regression function is like this. Let us suppose we have a sample and our regression line is like this. Then this is the wrong linear regression model and makes a wrong prediction, because the true relationship is like this. So we must be very careful about the specification of the function form. So linear versus non-linear. So these are the examples of linear models. This is linear both in variables and parameters. This is linear in parameters, but non-linear in variable. But we have made it linearized by taking its log. And this is also log-lin model, and this is a cubic model. These are the examples of non-linear statistical model, because here x1 is raised to the power beta 2, and here yi is raised to the power beta 2, and in this case the beta 2 xi is raised to the power e raised to the power beta 2 xi. So these are non-linear. These are various function forms. We have linear, log-log, semi-log. In semi-log we have linear log or log-linear, and then we have polynomial, and we can also have reciprocal or inverse regression model. So we must be very attentive to the forms of slope and elasticity. In these different cases, the slope and elasticity will be different from each other. In case of log-log model, this is a non-linear model, but by transformation we can linearize it, like y is equal to beta naught x raised to the power minus beta 1 e raised to the power epsilon I, and if you take log on both sides, then this model is linear. And we see, if you follow this, we equate this to beta naught star, and we equate this to y star, and we equate this minus beta 1 to beta 1 star, and log of x to x1 star, where beta 1 star is equal to minus beta 1. And if you take the derivative of y star with respect to x star, we get beta 1 star, and that is the elasticity coefficient. That is not, this is not a slope. This is proportional change in y divided by proportional change in x, or you can also say percentage change in y divided by percentage change in x. You can multiply by 100 here, and you can multiply by 100 here, and they will cancel each other. So that is why we can say that these are percentages are proportionate change in y divided by proportionate change in x. These are this is a quantity demanded and price. This is not linear, because here this is not linear in variable. This is the log-log model. Here the graph is linear. Here it is curvilinear. It is like convex to the origin. And if we have function form like this, when this is b is positive, then the function form will be like this. And again, for the log-log model, if here beta 1 is negative, here beta 1 is positive, so the slope of the regression line here is positive, here it is negative. Here is beta 1 is negative, so the slope is negative, and here beta 1 is positive, so it's positive. A semi-log model. A semi-log model could be log-linear model or linear log model. This is log-linear. Here is log and here is linear, so log-lin. But in this case, here is linear and here is log, so lin-log. And both of them are called semi-log. Here, alpha 1, if you take the derivative of log of y with respect to x, then alpha 1 is relative change in y divided by absolute change in y, and finally this will be equal to this. So, and similarly beta 1 is equal to absolute change in y divided by relative change in y. So this is dy divided by d log of x, and that will be equal to dy over dx times x divided by 1. This is polynomial, and one of the forms of the polynomial is quadratic term to capture non-linear pattern. So here we have x1 and x1 square. So if beta 1 is greater than 0 and beta 2 is less than 0, then the graph will behave like this. And if beta 1 is greater than 0 but beta 2 is also greater than 0, sorry, if beta 1 is less than 0 and beta 2 is greater than 0, then in that case the graph will be like this. This is inverted, this is like inverted U, and this is like U shaped. And if we have reciprocal or inverse transformation, then in that case we have the model like this. And here we will use xi star, where xi star is equal to 1 by xi. So these are some of the features of the reciprocal model. One is this: if beta 1 is if beta naught is greater than 0 and beta 1 is greater than 0, we have curve like this. If beta naught is greater than 0 but beta 1 is less than 0, then we graph like this. If beta naught is greater than 0 but beta 1 is greater than 0, we have graph like this. And if beta naught is less than 0 and beta 1 is less than 0, then we have the graph of the model like this. There are two conditions for nonlinear and non-additive equation transformation. Exists a transformation of the variable. Sample must provide sufficient information. There is example: suppose y is equal to beta naught plus beta 1 x1 plus beta 2 xi square plus beta 3 x1 x2. If you transform x2 star is equal to xi square and x3 star is equal to x1 times x2, and we will write the model like y is equal to beta naught plus beta 1 x1 plus beta 2 x2 star plus beta 3 x3 star. This is example 2, and if we transform, we will use x1 star, and x1 star is equal to 1 divided by x plus beta 2. So we will rewrite y is equal to beta naught plus beta 1 x1 star. However, x1 star cannot be computed because beta 2 is unknown. Application of functional form regression. One of the most widely used form of regression is that of Cobb-Douglas production function, and it is of the form y is equal to beta naught L raised to the power beta 1 k raised to the power beta 2 e raised to the power e raised to the power epsilon. And this model is linear in parameters, but this is non-linear in variables. So we can transform this by taking log on both sides. So natural log of y is equal to natural log of beta naught plus beta 1 natural log of labor plus beta 2 natural log of capital plus epsilon. So this implies natural log of y is equal to beta naught plus beta 1 natural log of L plus beta 2 natural log of k plus epsilon. And here beta 1 is equal to derivative of natural log of y divided by derivative of natural log of y, and this is the elasticity of output with respect to labor input, and beta 2 is the elasticity of output with respect to capital input. And the sum of beta 1 and beta 2 may either be greater than 1 or equal to 1 or less than 1. If it is greater than 1, we have increasing return to scale. If it is equal to 1, we have constant return to scale. But if it's less than 1, then we have decreasing return to scale. This is polynomial regression model, and one of the functions of one of the forms of polynomial regression model is marginal cost function or total cost function. And the form of this is y is equal to beta naught plus beta 1 plus beta 2 x square plus epsilon. This is marginal cost function, and this is the curve of the marginal cost function. And this is the polynomial function having a cubic function, and this is the total cost function. X appears as a absolute, a square, and as cube, and its graph is like this. So this is total cost function. Summary: the difference between slope and elasticity. Slope is change, absolute change in y divided by absolute change in x, and elasticity is proportionate change in y divided by proportionate change in x. In case of linear, beta 1 is equal to dy by dx, and elasticity is v1 times x divided by y. In case of log, beta 1 is proportionate change in y divided by proportionate change in y, and this is elasticity, where the slope will be equal to beta 1. This is the slope, and the slope will be equal to, this is elasticity. Beta 1 is elasticity, because if you take the derivative of this with respect to this, so we get dy over y divided by dx over x. So this is elasticity, and if we want to calculate slope dy over dx, then we will multiply this by y over x, then that will give us the slope. In case of log ln, beta 1 is equal to proportionate change in y divided by absolute change in x, and elasticity would be beta 1 times x. In case of ln log, beta 1 is equal to absolute change in y divided by proportionate change in x, and elasticity would be equal to beta 1 times 1 divided by y. So and dy over dx will be equal to beta 1 divided by 1 over x. In case of reciprocal model, beta 1 will be equal to dy over d over 1 divided by x, and that will be equal to dy divided by minus 1 x square dx, and that will be equal to beta 1. And finally dy over dx will be equal to beta 1 into minus 1 divided by x square, and its elasticity is beta 1 into minus 1 divided by xy. Here is the software output, eViews output of the linear model, where the dependent variable is GNP, and the independent variable is money supply M2. This is the coefficient of the constant. This is the coefficient of money supply. These are the standard errors, t statistics, and p values. And the estimated equation will be written as GNP hat, that is the estimated GNP is equal to 100.304 plus 1.5325 m square, and these are its t values, and the r squared value is 0.99, adjusted r square is 0.990, and here is the Durbin-Watson, and here is the f stat, which is also highly significant. This is the computer output, the eViews output of regression of GNP on the natural log of M2. So this is ln log model, and again these are the coefficients, these are the standard errors, these are the t statistics, and these are the p values, r squared, adjusted r square, and this is the estimated equation of GNP. And this is the case of log linear, where the GNP is in natural log and M2 is in linear. So the estimated equation is like this. This is the computer output of a double log model or constant elasticity model, where there is a log on the left hand side and there is log on the right hand side, and the estimated model is like this, and these are the t values, these are the r squared value and adjusted r squared value, f statistic and probability of f statistic. This is Durbin-Watson, and this is the another output where wage is regressed on unemployment rate, and the slope of the unemployment rate is minus. So the graph of the sample regression model of wage on unemployment has a negative slope, and this is the intercept, the same 10.34, and the estimated equation of wage is this. These are the t values. 4.862 is the t value for the intercept, minus 2.66 is the t value for the coefficient of unemployment. Remember, when the coefficient of the variable is minus, its t value will also be minus, because the standard error is positive, and if we divide this minus 3.8 by 1.4, which is positive, then the t statistic will be negative, minus 2.66. So that is why the slope of this line is negative. This is the output of the reciprocal model, and this is x star, where x star is equal to 1 divided by unemployment rate. So here now the slope becomes positive and the t value is also positive, and then this is the graph. This is the graph of this natural rate of unemployment, and this is the reciprocal 1 divided by x. and the estimated model is like this. This is the intercept from here, and its t value is from here minus, and this is the coefficient of x star, which is this, and this is reciprocal of x, and this is its t value from here. These are the r squared and adjusted r square values, and so on. This is the output of here natural log of wage and natural log of unemployment. This is double log. So here is the estimated model, and other statistics are here, and this is the again natural log of wage. Its constant is 1.90, and this is the natural log of reciprocal 1 divided by unemployment rate, and its coefficient is 1.175. These are the t values. So then we will take NT log of this, and that will be equal to 6.7113. Therefore it is a more meaningful and statistically significant bottom line for the minimum wage. NT log of 1.175, this is equal to 3.238. Therefore it means that 1 unit increase in X will have 3.238 unit decrease in the wage rate. This is the McCannon-White Davidson test for the functional form, and that is available in the Woodridge book on page 203. The procedure is, we will run OLS on the linear model. We will obtain y hat, that is the estimated value of the estimated equation. yi hat will be equal to alpha naught hat plus alpha 1 hat x1 plus alpha 2 hat x2, and then we will run OLS on the log model and obtain natural log of y hat, and that will be equal to natural log of y hat is equal to beta naught hat plus beta 1 hat natural log of x1 plus beta 2 hat natural log of x2, and then we will compute zi, where zi is equal to that should be y hat minus natural log of y hat, and then we will run the OLS on the linear model by adding zi to this, and that will be y hat is equal to alpha hat prime plus alpha 1 hat prime x1 plus alpha 2 hat prime x2 plus alpha 3 hat prime z1, and check t statistic of alpha 3 prime. If t computed for alpha 3 hat is greater than t tabulated, then we will reject h0, and the model is linear. And if the computed t for alpha hat 3 is less than t tabulated, then we will fail to reject h0, that the model is linear. MWD test for the functional form continued. Compute G2 NT log of natural log of y hat minus y hat. Run OLS on the log model by adding Z2, and check the t statistic for beta 3 hat prime. If computed beta 3 hat prime is greater than t tabulated, then it implies that we will reject h0, and that h0 is log model. But if computed t beta 3 hat is less than tabulated t, then it implies that we will fail to reject h0, that the model is log. This is the testing for the functional form of regression. So here we have y hat, and here this is y, this is x1, x2, and this is the coefficient of variation sigma hat divided by y bar, and its value is 0.064, and this is step 2. Run the log model and obtain natural log of y hat, the fitted and the estimated, and here the coefficient of variation is 0.0074. Then this is the step 4. True model is linear, and the coefficient of the z1 is 1.47, which is not significant. So we will compare the t computed with the t tabulated a 5%, and it implies if t star is less than t, then do not reject H naught. And if T star is greater than T tabulated at 10%, so reject H naught. This is step 6. The H naught is that the true model is log-log model. So the MWD test, T tabulated for 0.025 with 11 degrees of freedom is 2.201, and for 0.05 with 11 degrees of freedom it is 1.796, and T tabulated for 10% with 11 degrees of freedom is 1.363. Since T computed is less than T tabulated, so it implies that we will fail to reject H naught, and we will conclude that the true model is log-log model. And here we can compare coefficient of variation for the model 1 and coefficient of variation for the model 2. So criterion for comparing two different functional form is the coefficient of variation. It measures the average error of the sample regression function relative to the mean of y. Linear, log-linear, and log-log equation can be meaningfully compared. So the smaller CV of the model, the more preferred equation of the functional form. Say for example, this is model 1 linear model, and its standard error of regression is 2.12, but for the log-log model it is 0.021. So this is less than this one, so we conclude that this model is better than this one, that the function form must be log-log. So looking at these, we have 4.916 means that model 2 is better. Scaling and units of measurement. Let us suppose y is equal to beta naught plus beta 1 x plus epsilon I, where beta 1 is the slope of the regression line and beta 1 is the unit of change in y divided by units of change in x. So ultimately this is equal to dy over dx. And if y star is equal to 1000 y and x star is equal to 1000 x, then 1000 times y is equal to 1000 times beta naught hat plus beta 1 hat, 1000 times x plus 1000 epsilon I hat. So in that case we use y star instead of this, beta 1 star hat instead of this, beta naught hat star instead of this, beta 1 hat star instead of this, and epsilon hat star instead of this. Changing the scale of x and y. Let us suppose yi is equal to beta naught plus beta 1 xi plus epsilon I, but then we divide the whole equation by k, so we change the scale. So now we have yi star is equal to beta naught star plus beta 1 xi star plus epsilon I star, where yi star is equal to yi divided by k and epsilon I star is equal to epsilon I divided by k. Beta naught star is equal to beta naught divided by k, and xi star is equal to xi divided by k. So r squared and t statistics are will have no change in regression results for beta 1, but all other statistics are changed. And you can see the comparison here. Beta naught hat is equal to this here, and beta naught star is equal to this whole. So you see there is a change in the intercept, but slope is the same. Slope is the same, but there is only change in the intercept because of the changing the scale. And here we only change the scale of x and scale of y remaining the same. So we just divide this by k. This we multiply beta 1 by k, and we divide xi by k. So here yi is equal to beta naught plus beta 1 star xi star plus epsilon I, where beta 1 star is equal to k beta 1 and xi star is equal to xi divided by k. The estimated coefficient and standard error will change, but the other statistics will remain unchanged. So one is this and one is this. The intercept remains the same, but the slope of the line will change because of the change in scale of x variable. But if we only change the scale of y, then in that case we have yi divided by yi is equal to beta naught plus beta 1 xi epsilon I, and here we don't divide xi by k, so we only change the scale of y. So in that case we have yi star is equal to beta naught star plus beta 1 star xi. We don't write x1 star because we haven't changed the scale of x, we haven't divided this by k, so that is why we have xi plus epsilon I star, and these stars are explained here. So all statistics will change except for the t statistic and r squared. R squared and t statistics will remain the same, but all the coefficients will change. You see the intercept is changed and the slope is also changed, but the t value and the r squared value will remain the change. Effects of scaling and units change. T statistic, f statistic and r squared will not be affected. All properties of OLS estimations are also unaffected. The values of beta I, standard error of estimate, and regression sum of squares, residual sum of square will be affected, but t statistics, f statistic and r squared will not be affected, and all other properties of OLS estimators are also unaffected. This is the output. Let us suppose both the dependent and independent variables are in billions of $1972, then this is the estimated equation, and these are the t values for the intercept and the explanatory variable coefficient. This is the t value for the explanatory variable coefficient, and let us suppose we estimate this model, but here we change both the scales and these are in millions. So now you see the coefficients are the same and the slopes are the same. See, and this is when we when one is in the billions and one is in millions. So then we have this. Now you see this is changed, the intercept is changed, and the coefficient is changed, and the t values are still the same. The ex post and ex ante forecasting. For example, suppose you have a data on C and Y, that is consumption and income from 1947 up to 1999, and the estimated consumption expenditure for 1947 up to 1995 is like this. CT hat is equal to 238.4 plus 0.87 YT, where this is 0.87 is a marginal propensity to consume, and given the values of Y96 is equal to 10,419, and for the 97 this is 10,625, and so on. So the calculated predictions are the ex post forecast are, we will put these values in Y and we get these values for the 1996 consumption expenditure, 1997 consumption expenditure up to 1999 consumption expenditure. The calculated predictions are the ex ante forecast based on the assumed value of Y 2000 is 12,000, and then this is the estimate, this is the ex ante forecast equal to of consumption equal to 10678.04. Ladies and gentlemen, today's video is lecture number 8 in the series of various videos on introduction to econometrics, and we discussed regression model without intercept, that is we suppressed the intercept term, then we saw the results, and then we used various functional forms of the models, that is linear, linear log, log, reciprocal, and polynomial. And then we also discussed scaling and the units of measurement, and we compared the results of the regression. This is very interesting, ladies and gentlemen. If you like this video, you must share it with your friends, with your colleagues, and with students. And I dedicate this video again to Dr. Bilwan Singh Hung, because these slides were prepared by him, and he has done a very interesting job, very hardworking person, and I appreciate his contribution to econometrics. So I dedicate this video to Dr. Bill, and I just used his slides for explaining these concepts for my student, for my colleagues. I thank you all for watching this video. Ladies and gentlemen, don't forget to subscribe to the channel and click on bell icon so that you can get notification about my other videos in future. Thank you, and have a good night.